So thank you so much for having me. I'm super excited to give this talk today. As was mentioned, my name is Dr. Tropp. I just got my PhD in polymer science and engineering. And after listening to some of those last talks, I can see that, we've talked about polymers a couple times today. And I wanted to talk about a really exciting topic that we generally don't get to talk about until maybe even after college. I never heard of a sensor until I was actually in graduate school or really thought about them. But what's really cool about sensing technologies, especially with today's the topic of today, is that it's really at the interface of STEM. So it includes science, technology, engineering, and math. It puts all of it together. And I'm going to make the bold claim that sensors is where all learning begins. So let's go here. So a sensor is just something that measures a physical quantity, something you could put a number behind, and converts that into a signal that can be read by people or machines. And learning is just gaining knowledge or skills through experience, study, or being taught. Well, that knowledge comes to us through sensors. So here we are, we're learning about STEM, and this is what enables sensing technologies, which provide the signals that allow us to learn about the world. And this lets us take care of the environment, of each other, lets us provide energy, resources, and keep each other safe. So almost everything is really brought to you by some sort of sensing technology. So we're having a conversation right now. There's several different sensors at play. We have our human sensors, like our nose that lets us smell, and our skin, which lets us feel and touch. We have our ears that let us hear. We have our eyes that let us see. In our mouth, we're able to taste. But right now, we're not even in the same room, and we're still communicating. So there has to be some other sensor that's going on. And we have a microphone, we have a camera, and we have a keyboard and a mouse that are acting as sensors for us to communicate. I'd like you to take a second and just think, what other sensors are at home with you right now? As you look around, you may notice a smoke alarm. You may notice a thermostat that lets you control temperature, or a security alarm that detects motion. You may have a scale that detects weight. And you may have an Amazon Alexa that I just voice activated for you. But these are just a couple of the sensors that are around your house. And after this talk, I want you to go around your house if you can, and just see if you could find some sensors that you never really recognized were there. So how do these sensors work? Well, we make sensors by interacting with matter. Well, matter makes up everything. We start with our atom that is composed of electrons, which are negative, and in our nucleus, we have a proton, which is positive, and a neutron, which is neutral. And if we take a bunch of these atoms and we squeeze them together, we can get a molecule. And if we string these molecules together, we get those polymers that everyone has been talking about today. And these make up our clothing. They are used for drug delivery, as that last talk had brought up. They can be used for all sorts of things. They're in plastics. You yourself are made up of polymers, so proteins, carbohydrates, and nucleic acids. They're all polymers. And then we have lattices, which I believe there was a talk earlier that was talking about crystals. And crystals are lattices. So salt, for example, is a lattice. It's just a really well-arranged series of molecules. And we interact with this matter to make our sensors. So we have 4 fundamental interactions, which come to us through physics. And we have the gravitational interaction. So this is why we're not flying off the Earth. We're being pulled down towards the center of the Earth through gravitational interactions. We have electromagnetic interactions. So this allows for light, electricity, magnetism. And we also have the strong force. This is what keeps together the protons and the neutrons in the nucleus. And then we have the weak force. And this allows for things like radiation and radioactive decay. So we just make sensors by using one of these 4 interactions, or a couple of them at the same time, with matter. And as you see in the bottom, I bring up physics and chemistry because that's what we're primarily talking about here. But as we go through the talk, that list will expand quite a bit. We have gravitational forces. So this gravitational interaction is used in scales. So if you go to the grocery store and you see one of these scales that have a basket, you take fruits and things of that nature, you put it in here, and it compresses a spring, which we could then relate to that force. So we're able to weigh fruits and other foods at the supermarket through this weight sensor. Well, your digital scale at home works in a really similar way. Instead, when you step on this scale, it deforms a material And then that deformation, that squeezing, will actually create an electrical signal that we then relate to the wave. And funny enough, that's actually how your touch sensors work. So you have little sensors that are in your skin, and when they get pushed upon, they actually create an electrical signal that instead of getting processed by a computer, they get processed by your brain. So your skin works very similar to how a digital scale works. So that's gravitational interactions. And as you can see, we're bringing together engineering and neuroscience and biology. Well, what about electromagnetic interactions? So it was brought up earlier, and I know it's weird, but light is a wave. And the different colors are actually just different shapes of that wave. And that's what we are reading when we look at a camera. So a camera is taking in those different wavelengths, those different shapes of those waves, and getting processed by a computer. But our sight works the exact same way. We're taking in that light, and our brain is processing electrical signals that are created at the back of the eye. So this is using these electromagnetic interactions. So let's try another one. So vibrational sensors are a different type of sensor, but unlike those light waves, these sound waves need to move through something. So light can travel through space. That's why we can see stars. It doesn't need something to go through. But sound waves need something to move through. So if you've ever been in a pool and tried to speak to each other or make sounds underwater, you could hear it if you're both in the water. But if one of you's out of the water, you can't hear it because the sound wave is just particles bumping into each other, and you need to be in the same medium. So what are we using right now that operates through a vibrational sensor? And that would be a microphone. There's a little diaphragm, a little material that will actually vibrate when sound waves hit it and convert that to an electrical signal that then gets processed by a computer. You may see something repeating here. So what else works through that same process? Our hearing, our ear. So you actually have an eardrum that will vibrate, and then those vibrations will go through a bunch of little bones in your ear, and that will eventually be converted to an electrical signal that then again gets processed by your brain. And this, again, vibrational sensors are because of molecules bouncing into each other, and that requires several different fundamental forces all acting at the same time. But for my last class I was going to talk about today is my favorite class of sensors. They're called chemical sensors. And these operate on a little chemical reaction that occurs somewhere. So on our tongue, we have thousands of taste buds. And in the back of our nasal cavity, we actually have hundreds of different receptors. These are so cells, and in the cell wall, in the cell membrane, you actually have these little proteins that'll interact with these different chemicals. And when they interact, when they chemically react with each other, they'll create an electrical signal that interact and go to your brain. So we are processing little chemical reactions that occur on thousands of taste buds on your tongue and up in your nose all the time. So a quick comparison of a lot of the stuff I brought up so far. We have living organisms, people like us, and we have a signal that's created. So here we have at our nose, and then that signal is communicated through a nervous system, which then gets processed at your brain. Well, in machines, we have a signal conversion here at a microphone, and then we communicate that through circuitry or wires, and then that information gets processed at the computer. So it's very similar to how our sensors work. So now we're trying to come up with more unique chemical sensors that could detect other threats. We try to make artificial sensing organs to detect threats. Our senses are not quite good enough to detect different threats that we need to be able to detect. That's actually why for the longest time, and even still now, we use dogs that have better noses than we do, and they could actually detect certain threats that we can't. But even they don't have the capability to detect certain threats. So with water pollution and air pollution, in different medical related threats, when you go to the airport, they're testing for different chemical threats. Maybe you want a sensor for your food to see if there's any toxin in it. We really need new chemical sensors that give us insight and knowledge to things that we don't have currently. So when we design a chemical sensor, we're trying to do what a normal analytical chemistry lab does. So here I have a picture of an analytical chemistry lab, and it's huge, and there's all this equipment in it. It's not portable. This thing is staying put. It requires years and years of training, tons of money, and it's just not practical if you're trying to detect an environmental sample or trying to sense something in an environmental sample. So what we try to do, and what a lot of my research involves, is trying to make mini little devices that are portable, that are easy to use, and much less expensive. So a lot of my research, I just finished my PhD, was on making different types of environmental sensors, because I live by the Gulf Coast. The Gulf of Mexico is the 9th largest body of water on the planet. And a little while ago, there was an explosion at the Deepwater Horizon site. We know it as the BP oil spill. And there were a lot of toxic chemicals that were thrown into the water, and we don't really understand the impact that those chemicals have on us and the environment. So I went out on a boat through the school. This is the USM Point Sur. And we went out and we would test water samples to try to understand how much pollutants are in the water. But the problem is that you cannot fit a lab onto one of these boats. It's too big and the boat's too small. So we really needed miniaturized devices or some sort of experiment that we could do on the boat. So we want to develop chemical sensors. So we need to have a chemical reaction that creates some sort of signal. So what signals can we create with a chemical reaction? You may be familiar with some of these. There's something like color. So you could have two things interact and they make a color. You could have something that then glows, or what we call fluoresce. You may have seen glow sticks, for example, is a good example. You're making two molecules interact. Heat, or if you've ever seen a heat pack, when you smack it around and you break it up, you're making a chemical reaction occur and you're creating heat. You can make a magnetic response or an electric response. When these two molecules interact, you can maybe make something change size or weight. And remember, all of these could change with respect to time. And one of the most fun things about being a chemist is that we get to mix and match and be creative. Can we make something that glows and then convert that to an electrical signal? We get the freedom to really play with the molecules. So my chemical sensors operate through a polymer. Again, a polymer is just a bunch of these small molecules strung together in a line. We've heard about them a little bit today. And unlike other people's polymers that are, let's say, transparent or used in clothing, my polymers are colored and they glow. So I use these polymers and I design them, I engineer them to glow or not glow whenever one of these pollutants touches them. So here is an image, an artistic image of my polymer here. And I carefully crafted these arms that come off the polymer and will grab pollution out of the water. And when you do so, you can make the polymer glow or not glow, which is really cool. And as you can see, if they're in vials, you can see this solution of seawater turn on and off and on, so you can see if the pollutant is present or not. And it's really specific. So if I take other common pollutants that you would find in seawater, none of them turn on my polymer, because we carefully used organic chemistry to make little hands that come off the side of the polymer to only grab the pollutant that I want. In this case, it's actually a nutrient that feeds algae. And when the algae eat too much of it, it could destroy an ecosystem. So having a sensor that detects for this pollutant is actually really necessary. And what's nice about this, this test is that this fluorescence, this glowing, there are portable instruments that are available for scientists to throw in their bag. They could go on site and they could test these right then and there. And we create these little calibration curves to let them know how much glowing corresponds to how much of the pollutant. So they're able to, on site, right there on the boat, they can know exactly how much of these pollutants are there. And we've made these sensors for all sorts of toxic metals. We've made it for different nutrients. We've made it for some molecules that come from the burning of fossil fuels over the last couple of years. So before we get done today, I really wanted to bring up the history of sensors, because there's a lot of chemistry and physics and biology that allow for us to even make sensors. And the history of sensors is really just the history of STEM. So in the 1600s, the scientific method was developed by Francis Bacon. And after that, shortly after, was the discovery of the cell, and then gravity, electricity. And almost 300 years later did we really start getting an understanding of things that really started chemistry, like what an electron was, or the first models of the atom, the chemical bond, quantum mechanics. But one invention that we don't necessarily talk about that I think was really important was that of the integrated circuit. This was developed by the same people that make our calculators. And it was once this circuitry was able to be made and made small that we were really able to take what we'd learned from the last couple hundred years and incorporate them into small little devices that we could then use to make portable sensors that make our lives better. So I call the late 1900s now really the age of sensors. And I can't bring up all the different examples that are really important, but here we have a pacemaker that's able to detect the beating of your heart. And if there's something wrong, it can help fix it. We have the pregnancy test. If you know anyone that's diabetic, or if you're diabetic, we have the blood glucose monitor. I mean, I don't know how many lives have been saved because of the blood glucose monitor. There's the Fitbit. This is a really cool example, not because it's as important as the other three, but you can see that there are things that you buy or may want to buy on a regular basis to give you information about your health. And what's really exciting about right now is that we have all of this knowledge available to us to engineer and come up with new sensors to make people's lives better. So right now is a wonderful time to enter science. So there are a bunch of different resources I want to make available to all of you. If you're interested in sensors or science or whatever, we have Arduino. So this is these do-it-yourself kits to teach you about programming and making actually electronic sensors. They're really wonderful. I'm trying to figure it out myself, actually. There's another version from Lego Engineering that's a little bit more intuitive. There's Project Gutenberg, which I like to bring up just to people in general. Most of the books you may read for a lot of your classes are really old, like 300, 400, whatever many years old. And a lot of them are actually free. So this is actually a digital archive to get you access to famous books that you may need to read for your classes. OpenStax is a wonderful resource. It's free digital textbooks on like calculus and like, all the maths, physics, chemistry, biology. It's a wonderful organization. It's low cost if you buy it in print, but the idea of just getting free textbooks on stuff that you would want to learn is pretty cool. Khan Academy is a wonderful resource. Wikipedia, usually you want to be hesitant about, but for science, it's pretty good. It's a nice place to start if you want to learn something. There's a lot of really good YouTube channels. I like Vsauce and Kyrgyzstan for a place to begin. But of course, go to your teachers, your parents, and even scientists like me if you ever have questions or want to figure something out. But I would like to acknowledge, of course, the whole Expanding Your Horizons crew for giving me the opportunity to talk to you all today. I have a lot of friends in Cornell. I'd like to thank them. And of course, the TechBridge Girls for sponsoring this, and then the National Science Foundation for sponsoring me, and the University of Southern Mississippi, where I currently work as a postdoc. And all of you for your attention. I know it's been a long day. And here are some images from the internet. You always want to cite your sources. So here's where I got all those images from. And I would love to take any questions.
Thank you so much, Dr. Tropp. That was a great talk. Ooh, sensors, amazing. They contribute so much to our lives. Let's see. So, okay, my name is Sana, and I'll be asking some of the questions that our participants have for you. Let's see. Oh, hi. I didn't know my camera was off. Here we go. So Irene is asking if the four interactions, the ones you mentioned, gravitational, electromagnetic, strong force, weak force, are the only ones that exist, or are there any other force interactions that exist?
So the ones that have been confirmed by physicists are those four. When I was getting ready for this talk, I went to the Wikipedia page on the four fundamental forces, and there was an argument about a fifth, and it was a little bit over my head, to be perfectly honest.
Okay, so it's getting updated. Yeah.
Yes.
Great. Okay, let's see. Oh, and then Giacomo is asking if you briefly discuss the type of sensors that are used for the Internet of Everything technology.
Yeah, so there's a lot of different types of sensors. One that I didn't go over here are field effect transistors, and they are a special type of layering of polymers, just like the ones that we were talking about earlier, that conduct electricity. And they are usually mixed together with different metals. And they're what's nice about them is they're really, really, really tiny, and they make a little electrical signal. So those are usually incorporated to things that are able to communicate with each other. And that would be, if you wanted to Google something, field effect transistor might get you to where you're trying to go.
Okay, I guess somewhat related to it. I don't know if, let's see. And Sadie wants to know what sensors does Amazon Alexa use? So would Alexa have some of those transistors too?
Yes, and actually what's really funny, on that resource I provided from Arduino, you could actually make that electrical voice activated sensor on a little kit that they sell from their website.
Wow.
If you want to make that and get it to work and then plug it into your computer through USB, you can get it to work.
Oh, that's gonna be a cool project for our participants here. Okay, so this is a great question. What are the challenges of scaling sensors to be small versus large?
It's a really, really good question. So there's a lot of different types of molecules. We talked about the small molecules, the polymers, and the lattices. And there are different classes even between those. And the choice of which molecule to use for your sensor is a lot of the times based on size. So what's nice about those field effect transistors is that you could print a bunch of them at once. And that's why, for example, Intel and other companies will use those. So for a lot of applications, it's going to really be these integrated circuit based sensors. But for small scale sensing technologies, sometimes you need something that maybe has some tricks up its sleeve that those just can't do. So that's where some of my polymers could actually be used, because not as much of it needs to be made. And for example, the little polymer I made that glows, you use a millionth of a gram to do your sensor. So if you could make a couple grams of these polymers, which is very possible, you could theoretically make hundreds of thousands of these little tests. So they're pretty available.
Yeah, so make it widely available for people to use. That's great. Wow, cool. Let's see. Another question here is, I think you mentioned some of these websites already, but a lot of the two different people from Canada, Artesh and Arush from Canada, are asking, is there any software or websites that you may recommend where they can simulate some of the chemical sensors and understand how they work?
Ooh, chemical sensors, that's an interesting one. I know a place that you could start. There's a journal called the Journal of Chemical Education. And they have a series of articles on making do-it-yourself chemical sensors at home.
Oh, wow.
So Journal of Chemical Education, and I know those ones are open access. Those are free to open. I use them a lot.
Okay, great. Oh, and then we can definitely post these links to the resource pages on our website, the UIH website, so people can feel free to go there, take a look at, and then do mini projects while they're at home.
Yeah.
That's great. Okay. Here are some questions. I guess the Alexa question kind of made people wonder about these other things too. So Mara is asking, how do Fitbit sensors work?
Okay, so I'm not super familiar with how Fitbit sensors work, but my guess, there's two different types of ways that a lot of those healthcare technologies will work. So we talked about different wavelengths of light and the different shapes, and it had been brought up earlier that some we can't see. So many of these newer technologies are actually working on what's called near-infrared wavelengths, which can penetrate your skin. So you could get information about things in your body without actually entering your body. So it's either that, or it's detecting, small changes from your heart rate. And it's
Okay.
just right there on it.
Mm-hmm.
But I've never owned a Fitbit, but all my
Oh,
friends have one.
mm-hmm. Yeah, it seems to do a lot of different things. I also don't have a Fitbit, but yeah. And then, oh, Margot is asking, smoke detectors are sensors too?
Yeah,
Okay.
they are all sensors. There's some people will not like the term sensor unless it processes the data for you and gives you a plot. But
Oh.
the most broad definition of a sensor is something that converts a signal into information that's useful. And if
Mm-hmm.
it starts beeping and telling you there's a fire, to me, it just sends something for me.
Mm-hmm. Right. Yeah, those are, oh, I know we have so many other questions that I think hopefully you could probably answer them at the through the chats.
Sure.
Okay, great. Oh, that was a great talk. I didn't know we have sensors all around us. Oh, thank you so much, Dr. Tropp.
No problem.
That was so wonderful. We just loved it. Thank you so much. And we love your slides. So everybody's just over the moon about your slides. So we might be asking you for that template.
Sure.
Because I think a lot of us are just blown away. So cool. So fun to see that. And it's just so fun to have people involved from all over, which is kind of the silver lining to EYH this year, is getting to bring you in and bring in some of the other speakers that we've had throughout today. We just love it. So thank you so much for that talk, for reaching out. We were so excited to have you. And if you ever are brave enough to venture up to upstate New York and you're not too thrown off by the fact that it snowed in April, we would, of course, love to see you up here at Cornell in person as well. I think a lot of us would love to meet you and chat and hear some of your wisdom and insights. So thank you so much.
I appreciate it. Thank you so much.